Welcome to the Explainer. Today, we're jumping right into a pretty fascinating conflict that's playing out at the absolute cutting edge of AI. We are talking about a massive, groundbreaking paradigm shift in how artificial intelligence actually learns from structured tabular data. Okay, let's dive into this. Now, I want you to consider a bit of a provocative question. Why exactly is tabular data widely considered the last unconquered castle of deep learning? I mean, think about it for a second. AI has already, effortlessly conquered images. It can recognize faces in a crowded street in a snap. It's totally mastered text, writing full essays and translating languages in milliseconds. But basic rows and columns, they remain stubbornly, almost frustratingly difficult for deep learning models to process effectively. Today, we're going to unpack exactly why that is and look at the ingenious new architectures battling to finally conquer this space. So, here is our roadmap for today. We'll quickly cover the tabular data challenge, look at the generative heavyweights, check out the diffusion approach, and then explore the STAB paradigm shift. After that, we'll compare STAB versus traditional models and wrap up with the future of tabular AI. All right, Section 1, the tabular data charge. Tabular data, you know it well. Rows representing instances, columns representing features. It is literally the lifeblood of major industries. We're talking about everything from patient health records to complex financial transaction logs. It is everywhere. It's really fascinating to consider the complexity under the hood of how an architecture like TabNet handles this using sequential attention. It's kind of like a giant puzzle. Unlike an image where pixels share obvious spatial relationships, tabular features, things like age, work class, education level, capital gain, they're just a chaotic mix of totally unrelated concepts. A model has to somehow learn exactly which specific subset of these highly varied features to actually pay attention to at every single decision step. Which brings us to the core, unique challenges of this data. First off, tabular data is highly heterogeneous. You've got this messy mix of continuous numbers and discrete categories jammed together. Second, those discrete classes are frequently deeply imbalanced, which heavily biases models. But the absolutely biggest challenge? The total lack of spatial or semantic structure. Think about it. If you have an image of a cat, you can easily create more training data by cropping the image, rotating it, flipping it, whatever. But there's no way you can simply crop a person's age. You can't rotate their marital status. Traditional data augmentation techniques completely fall apart here. Moving on to Section 2, generative heavyweights, VAEs and GANs. So, how have researchers traditionally attacked this unconquered castle? Well, mostly by bringing out the siege weapons, using heavy-duty generative models to brute force synthesize new tabular data. One of the first major tools used is the TVAE, or Tabular Variational Autoencoder. This probabilistic model takes your raw tabular data and uses an encoder network to essentially map it down into a compressed, latent space representation. Right there, in that hidden space, it captures all those complex dependencies between your varied columns. Finally, a decoder network attempts to reconstruct the original input from that latent representation. By minimizing the reconstruction loss, it slowly learns the underlying distribution of your whole spreadsheet. Now, what's really interesting here is how the next heavyweight, CTGN, handles that imbalanced data problem we discussed earlier. CTGN, which stands for Conditional Tabular Generative Adversarial Network, uses adversarial training. It pits a generator directly against a discriminator, but the real genius here is the conditional part. To prevent the model from just ignoring rare categories, like, say, a rare disease in a patient record, it uses conditional vectors. It essentially forces the generator to synthesize samples conditioned on those specific, imbalanced categories. This makes sure the final synthetic data perfectly preserves those vital feature dependencies. It's a really clever trick. That brings us to Section 3, the diffusion approach, specifically TabDPPM. Recently, the whole AI world has been absolutely dominated by diffusion models. Enter TabDDPM. This approach takes the exact same denoising magic that generates photorealistic images and miraculously applies it directly to tabular datasets. The basic idea is that the model learns the data distribution by systematically adding noise to the tabular data until it turns into complete gibberish. Then, it learns how to perfectly remove that noise to generate brand new, highly realistic data points. But wait, remember our tabular heterogeneity problem? You can't just add standard static noise to categorical text. TabDDPM elegantly splits its diffusion process to handle this. It uses Gaussian diffusion to add and remove noise from continuous variables, things like pricing or age. But for categorical variables like an occupation or a country, it switches over to multinomial diffusion. It is a highly effective, albeit pretty computationally complex, brute force way to model the exact distribution of the original dataset. All right, Section 4, the STEEB paradigm shift. So we've seen how to generate synthetic data using brute force. But what if we abandon that approach entirely? What if we could learn the representations natively without creating any fake data at all? This concept from the creators of the STAB framework hits the nail right on the head. Because tabular data lacks spatial structure, trying to randomly alter, mask, or corrupt inputs to force the AI to learn, which is exactly what contrastive generative models usually do, well, it's inherently flawed. Corrupting a spreadsheet often just destroys the underlying relationships entirely, and that leads directly to representation collapse. So the absolutely crucial point is how STAB bypasses this whole mess entirely. STAB is an augmentation-free, self-supervised framework. Instead of corrupting the input data, it feeds a single, totally untouched input into two weight-sharing encoders. To create variance, it applies something called drop connect. Now, instead of dropping data, drop connect stochastically drops the connections within the neural network layers themselves. It alters the model, not the data. And by using stop gradient operations, it ensures the representations don't just collapse into a trivial solution. It is a frankly brilliant use of network regularization over traditional data augmentation. Now for Section 5, stack versus traditional models. Let's see them head-to-head. Traditional generative models and standard contrastive learning rely really heavily on data corruption. They require complex adversarial or diffusion training loops, and they often rely on finding positive and negative pairs of data. That is computationally expensive and really difficult in dense tabular spaces. Conversely, the STAB framework is entirely augmentation-free. It uses stochastic regularization, specifically that drop connect feature we just talked about, to act as the variance. It learns robust invariant representations without ever relying on negative pairs or synthetic corruptions. It's a lot leaner and theoretically much more aligned with the actual nature of rows and columns. But does it actually work in practice? Absolutely, for sure. When we look at the empirical classification accuracy results across some diverse real-world datasets, the numbers speak for themselves. Compared to SCARF, which is a really strong traditional baseline that uses input corruption, STAB consistently outperforms it. On the robot dataset, we see a massive jump from 83.5% to over 88%. On the theorem dataset, a jump of 4 full percentage points. The data literally proves that using stochastic regularization inside the network is a vastly superior approach for modeling invariance in tabular settings compared to randomly augmenting the input data. Which leads us to our final section, Section 6, the future of tabular AI. We've seen the battle lines drawn today between traditional brute force generation and this elegant self-supervised representation learning. I want to leave you with a final thought to consider for your own work. How will you rethink your tabular data pipelines now that you know the true power of representation learning over brute force generation? If you're out there struggling with imbalanced, noisy tabular data, the answer might not be generating more synthetic noise. The answer might just be utilizing elegant, augmentation-free frameworks like STAB to finally conquer your own tabular data castles. Thank you so much for joining me for this explainer. I really hope this helped clear up this complex and super exciting frontier in AI.